Hello and welcome. Introduction. In this video, I'll show you how to use the UART communication module of the TM4C123GH6PM microcontroller. UART communication. Now, UART stands for Universal Asynchronous Receiver and Transmitter. It is a serial communication protocol used to transfer data serially between two devices in embedded systems. Now, it is an asynchronous communication protocol. What that means is that no clock signal is required for synchronization between two devices. Now, before I go any further, let's briefly review what serial transmission is. So here I have a series of bits. Now, serial transmission is transmitting a sequence of bits in a continuous stream as depicted here. Now, the least significant bit, that is D0, all right, it is the first bit is transmitted. Now, before this gets transmitted, we have a start bit. So start bit is the first to go, followed by D0, D1, D2, and so on. And the last bit of the information is D7, but that is usually followed by a stop bit. So stop bit is the last bit to go. So quick recap, serial transmission really is transmitting a series of bits like this serially. Now, in this example, D0 to D7 represent the uppercase A. The TM4C123GH6PM UART. Here is the TM4C123GH6PM microcontroller high-level block diagram. I've taken this block diagram from page 48 of the TM4C123GH6PM microcontroller datasheet. And here I would like to highlight this serial peripheral block. And let me zoom in. And as you can see, the TM4C123GH6PM microcontroller has 8 fully programmable UARTs. And here are the 8 UART modules with the pin allocation. Okay, so for example, let's take a look at UART 0. All right, so UART 0, the RX pin or the receive pin is allocated port A bit 0, that is PA0, and the transmit pin, TX pin, has been allocated port A bit 1, therefore it's PA1. Now, and then there are UART 1, UART 2, and so on, and up to UART 7. So altogether, including UART 0, there are 8 UART modules. Now, I would like at this point to highlight UART 5. And UART 5 has a receive pin. It's been allocated PE4, that is port E bit 4, and the transmit pin of UART 5 has been allocated PE5, that is port E bit 5. Take a note of this because this is the UART module that I'll be using in this video. Okay, let's take a look at the UART module block diagram. I've taken this block diagram from page 894 of the TM4C123GH6PM microcontroller datasheet. Now, here are some of the registers in the UART module that I'll be using in my program later. So the first one is I like to look at is the clock control part, and like to highlight these two registers here. The first one is the UARTCC. That is the UART clock configuration register. Then there is the UARTCTL. That is the UART control register. Next, I want to take a look at the control status part, which is this bit here. And I just highlight the UART flag, which is the UARTFR, and then the UART line control register, which is the UARTLCRH. And then for the bulk rate generator, there is the UART integer bulk rate divisor, which is the UART IBRD register, and then the UART fractional bulk rate divisor, UARTFBRD register. Hardware connections. Let's take a look at how we can connect a laptop or a desktop to the TIVA C-Series Launchpad board. Now, in my case, I need to connect my laptop to the TIVA C-Series board via using the USB port on my laptop. All right, so I need to connect from using the USB port here to PE4 and PE5 pin, which is the UART 5 module. Now, in order to do that, I need a USB to TTL adapter cable as shown here. All right, so here is a block diagram of the overall connection. So from the USB port of the laptop or computer, using the cable, USB to TTL cable, I can then connect it to the TIVA C-Series Launchpad board. Now let's take a closer look at these connections here. All right, so the red connection is the 5 volts. The black connection is the ground, GND, and the white connection is the TX or transmitting cable, and the green cable here is the receive pin or cable. And here is the launchpad board. And I like to focus on this part of the board. And let me zoom in here to this part. And let me just turn it round like here. And I connect the green pin of the cable of the cable to PE5 port E bit 5, which is this one here. Notice there are two rows of pins. All right, so this pin here is PE5, and the white cable here pin is connected to PE4 port E bit 4, which is this one here, and then the black cable is connected to the ground GND, which is this row, this pin here on this row here. All right, so these are the three connections. Now the red, you don't have to worry about the 5 volts because the board will be powered via the USB connection to the laptop. So we don't need to connect this. All we need are these 3 connections. Here is my particular setup. The program. Full listing. Okay, so what I'm going to do is to first of all show you the full listing of the entire program. And then in a few moments, I will explain the details to you. So let's look at the start of the program here. We have the initialization part, followed by the definition of the registers with all its appropriate addresses. Then I have here the start of the main routine or main program or procedure, prog. It goes right up to this point here, where it says NDP. That's the end of the this main routine. Then follows the subroutines that are being used up here. All right, so here we call 3 different subroutines, and it starts here. The subroutine, the first subroutine is to enable the clocks. All right, it enables the clock to the UART5 module, then enable the clock to the GPIO port E, and then follows the next subroutine, initializing the UART. So initialize UART. Here in this subroutine, we disable the UART first, then set the baud rate of 9,500. This is called the integer part. We'll come to this in a few moments. Then we set the baud rate for the fractional part. Then we select the system clock. We set the data length. Then we enable the UART module. At the beginning, we disable so that we can set the baud rate and so on. Once we've done all that, we enable, and that ends the subroutine. Then the next subroutine is configuring the UART5 module. So configure UART5 subroutine starts here. We set port E bit F and port E bit 5 as digital. Enable the alternate functions because we're using the UART function. Then disable analog function. We configure PE4 port E bit 4, port E bit 5, PE5 for the UART. And here we then end the subroutine. Then the final subroutine, which is used to transmit the character to the serial terminal, is handled by this subroutine here, UART5_transmitter prog. And this here basically, as I mentioned earlier, is to transmit the character we want to the serial terminal. And here it ends the entire program. The program explanation. Okay, so here is the initialization section of the code or the program. So Arial, my code read only. Area is an assembly directive. All right, it is used to define a specific area in memory where the code is stored. All right, next, my code is a name that I have chosen. You don't have to call it my code, you can call it any other name. Then follow the code. Now, code here is an attribute of the area directive. Basically, it's an attribute that specifies that the section contains executable code. And then next is read-only. Again, read-only is an attribute of the directive area, and is an and it indicates that the section is read-only and cannot be modified at runtime. And then we have the export directive. Basically here, it says that the symbol here, __ main, is visible to the linker. And then finally, the entry directive marks the entry point of the program. Okay, next follows the definition of the register's addresses. Now, let's take a look at SYSCTL _ RCGC UART. Now, this symbolic name here basically is the name for the universal asynchronous receiver transmitter run mode clock gating control register. And I have assigned this hex value, which is an address, to this symbolic name here. Now, what I want to do is at this point is to look at how this address is derived. All right, so I've taken this from page 344 of the datasheet for the TM4C123GH6PM microcontroller. All right, so as you can see, this is the universal asynchronous receiver transmitter run mode clock gating control register, and it has an offset of 618. All right, and this is a 32-bit register, but only 8 bits are used. Here is the base address of which is hexa 400FE000. Ignore the dot. So this is the base address. All right, and if you add the offset 618 hexa to the base address, you get a resultant address of 400FE618, and that's the address that I have assigned to the symbolic name that I mentioned earlier. All right, this is how that address is being derived. Okay, so this is how all the other addresses are derived. You need to refer to the data sheet of the TM4C123GH6PM microcontroller datasheet. Okay, so __ main proc marks the start of the procedure or the main routine. Now the underscore main proc procedure starts with initializing the clock for UART 5 by using this instruction BL. BL stands for branch with link. Basically, the way I'm going to describe this is BL is can be described by calling it a branch to subroutine. All right, it basically describes what the BL instruction do. So I would now from here on I would say branch to subroutine, but the actual BL stands for branch with link. So please take note of that. So here we have a branch to this subroutine. Basically, that this subroutine will enable the clocks. We'll come to the details of this in a few moments. Then another BL instruction, branch subroutine to initialize the UART 5 module. And then there is a third BL instruction that would configure the UART 5 module. Then next, after the initialization part of the program then proceeds to transmit the message or this word hello with carriage return and line feed. So let's take a look at these two instructions here. So LDR, a load instruction, basically will load this hex value 48. Why 48? Because 48 is the hexa representation of the ASCII value, uppercase H. So this gets loaded or copied into register R0, and then we call a subroutine or branch to a subroutine UART 5 underscore transmitter. This subroutine will then transmit this to the serial terminal, and you'll see a H, and that gets repeated for all these other ASCII values, including the carriage return and line feed. All right, eventually you see the word hello displayed on the serial terminal. And here, a branch B loop that will send the program into a infinite loop. E and DP here marks the end of the main procedure. Okay, so we've come to this subroutine here, enable clocks prog. This is the subroutine, and the first 4 instructions of the subroutine basically is to enable the clock to the UART 5 module. Now, viewers of this channel would be very familiar with these instructions. So this first load, LDR, load instruction, will copy this address, this symbolic name has an address. Remember, we declared it earlier. So let me just remind you what this address is. Basically, the address is 400FE618 hexa. So this gets copied or loaded into register R1. The next LDR load instruction basically will copy the contents of the address pointed to by R1. R1 is pointing to this address, so the current content of this address will be loaded or copied into R0. Next is an ORR instruction. Basically, this performs a bitwise OR operation, OR operation on register R0 with the value 20 hexa. All right, and now 20 hexa corresponds to bit 5, which represent UART 5. Now, setting this bit 5 to a 1 enables the clock to the UART 5 module. And then the str instruction, store instruction, basically will copy or store the current value of our register R0 into the address pointed to by R1. Remember, R1 is pointing to this address. Next, we have the enable clock to GPIO port E instructions. So these 4 instructions will enable the clock to the GPIO port E. So again, if you notice, these instructions are identical to the one that we have seen earlier. So here we copy or load the address assigned to this symbolic name, and the value assigned or the address assigned is 400 FE608 hexa. So this gets copied or loaded into register R0. The next instruction, load instruction, LDR instruction, will copy the current contents of the address pointed to by R1. Remember, R1 is pointing to this address. So whatever is at this address, the contents of this address will be copied or loaded into R0. Now, the next instruction is an ORR instruction. As mentioned earlier, this is a bitwise OR operation with the contents of R0, and this value in this case is 10 hexa. Basically, this 10 corresponds to bit 4, which represents port E. Now, setting this bit here will enable the clock to GPIO port E. And then we come to this familiar STR instruction. Basically, this will copy the current contents of R0 into the address pointed to by R1. R1 is pointing to this address. Then we come to this BXLR instruction. Basically, this will return the control back to the main routine. And E and the P here signifies or marks the end of this subroutine. The initialize UART 5 proc subroutine, which is this subroutine here, configures the UART 5 module to prepare it for data transmission and reception. Now, these 3 instructions here disable the UART 5 module. Now, the purpose of disabling the UART 5 module is to prevent unintended transmission whilst configuring. So let's take a look at this first instruction. We should be familiar with this by now, but I'll go through it. So this is a load instruction that will copy the address of this symbolic name, that is 4001130 hexa. So that would be copied into or loaded into register R1. Next comes this MOVS R0, #0. Now, MOVS instruction in the ARM assembly language is basically a variation of the MOV instruction. Now, MOVS stands for move with update of status flags. Now, the S at the end of MOV indicates that the instruction will update the condition flags in the current program status register, the CPSR register. All right, and then finally we have this last instruction here, STR, which is a store instruction that will store the current value in R0 into the address pointed to by R1, and R1 is pointing to this address. Now, next comes with the next two basically sets of instruction, this one here and this one here, basically that will set the baud rate. Now, when using hardware with like the ARM Cortex microcontroller, the baud rate is set using two parts, the integer part and the fractional part. Now, I will not go into the details in this video because it would take too long, but just take note for this video that the baud rate is set using these two parts, the integer part and the fractional part of the divisor. So this part here, these three instructions here, deals with the integer part. So we come across again the familiar LDR instruction here. Basically, this LDR instruction or load instruction will load or copy this address, which is 400110024 hexa. We'll copy or load that into our register R1. And then this load instruction will copy this decimal value 104 into register R0. Now this value 104 corresponds to the integer part of the baud rate divisor for setting the baud rate of 9600. And then this store instruction will store the current value of R0 into the address pointed to by R1, and R1 is pointing to this address. Next is this part here that deals with the fractional part of the baud rate. So here we have the LDR load instruction that will copy this address 400110028 hexa into register R1, and then this instruction here will load this decimal value 11. We'll copy that or load that into register R0. Now this 11, this value corresponds to the fractional part of the baud rate divisor to achieve the 9600 baud rate. And then the store instruction will store the current value of R0 into the address pointed to by R1, and R1 is pointing to F0011028. Okay, let's take a brief look at some of the registers mentioned in the code explanation. Now, this is the UART control register, the UART CTL register. Notice the base address, the UART 5 base address is 40011000. Ignore the dot. So this is the hex value for the base address for UART 5. And notice the offset is 030 hexa. Now I've taken this from page 918 of the TM4C123GH6PM datasheet. Now, I'm not going to go into the details of all the registers because that would take up too much time. Now, I would encourage you to refer to the datasheet for more information. Now, I've given the link to the datasheet in the description. A quick note before we move on. This UART control register is a 32-bit register, like all the registers in the TM4C123 microcontroller. They are all 32 bits registers. Next is the UART integer baud rate divisor register. Now notice the UART 5 base address is identical to the earlier one, so it's 40011000 hexa, and the base address for this register is 024 hexa. Again, it's a 32-bit register. The register utilizes bit 0 to bit 15. And then the other UART register is the UART fractional bulk rate divisor register. Base address is 40011000 hexa, and the base address, the offset is 028. Only a bit 0 to bit 5 of the 32-bit register are used, and this is taken from page 915 of the datasheet. Okay, so the following instructions, the one in the red box, will select the system clock. So the first instruction here is the load instruction. So basically, as you would have guessed by now, this has a value assigned to it, all right, which is 40011 FC8. So that value, hex value, which is an address, that will be copied or loaded into register R1. And then this MOVS move instruction will copy or load this value 0 in decimal into register R0. Now this value 0 is used to select the system clock for the UART. Then the third instruction here, the store instruction, will store the current value of R0, which is this, into the address pointed to by R1. R1 is pointing to this address. Now, the next three instructions here basically set the data length, which is 8 bits, and there's no parity and no FIFO, first in, first out. Now, the load instruction here is identical to this one, but this symbolic name has this address, 4001102C hexa. So this will be copied or loaded into register R1. And then this move instruction here will copy this value, 60 hexa, into register R0. Now 60 hexa represents the configuration for 8-bit data length, no parity, and no FIFO. And then the store instruction here will store the current value of R0 into the address pointed to by R1, and R1 is pointing to this address. And then the last three instructions here enable the UART5 module, the transmitter and receiver. Now this symbolic name here has this value which was assigned earlier, and it has a value of 400110030 hexa. So this will be copied or loaded into register R0. And then we load this value, hex value 301, into register R0. Now this value will enable the UART5 module, enable the transmitter bit, and then enable the receiver bit. So this is the value here that does all that. And then the store instruction will store the current value of R0 into the address pointed to by R1, and R1 is pointing to this address. Then this next two instruction here, basically BXLR will return the control back to the main routine, and ENDP marks the end of the procedure or subroutine. Okay, let's look at the UART clock configuration register. And you can find this on page 939 of the microcontroller datasheet. For the UART 5 module, the base address for this register is 4001 1000 hexa, and the offset is FC8. It's a 32-bit register, but only bits 0 to bit 3 is used for this clock configuration. Then the next one is the UART line control register. You can find this on page 916 of the datasheet. And for UART 5 module, base address is 4001 1000 hexa. This is, as you notice, this is the same as the previous base address that we've seen for the other register. Then the offset for the UART line control register is 02C hexa. Again, it's a 32-bit register, but this time bits 0 to bit 7 are utilized for the UART line control register. Okay, so here we have the config UART 5 prop subroutine. So this whole subroutine here is responsible for configuring the GPIO port E pins, specifically port E bit 4, PE4, and port E bit 5, PE5 for UART operations. Now, these instructions here in this red box is to set PE4 and PE5 for digital input-output functions. So this load instruction here, by now we are all familiar with this, basically will load the address assigned to this symbolic name. Now the address for this symbolic name is hexa 4002451C. So this value or this address will be copied or loaded into register R1. The next load instruction basically will load the current value pointed to by R1. Now R1 is pointing to this, so it will load the current value of this address into register R0. So this is the function of this load instruction. Now the next instruction is the ORR instruction. Basically, this performs a bitwise OR operation with between register R0 and this hex value 30 hexa. Now 30 hexa corresponds to bit 4 and bit 5, which represents PE4 and PE5. Now setting these bits basically will enable the digital functions for PE4 and PE5. Next, the store instruction will store the current value in R0 into the address pointed to by R1. Now R1 is pointing to this. So the current value in R0 will be stored in this address. Okay, next we have this group of instructions here. Basically, these instructions will enable the alternate function for PE4 and PE5. Remember, the port E can be used for general purpose input-output function, GPIO, but in this case, we're using the port for UART operation. So we need to enable the alternate function. So here, again, our familiar load instruction basically will load the address assigned to this symbolic name, which is hexa 400244420. So this will be copied or loaded into register R1. And then the contents of this address will be copied into register R0. That's the purpose of this instruction. So this instruction will copy the contents of the address of the location pointed to by R1 into register R0. Next is our ORR instruction, which is a bitwise OR operation, right? Basically, this will perform a bitwise OR operation between R0, register R0, and this value 30. So 30 hexa represent bit 4 and bit 5, as mentioned up here. So setting these bits will enable the alternate function mode for these pins. And by doing that, we will enable the bit 4 and bit 5 for communication purposes. Next, the store instruction will basically store the current value of R0 into the address pointing to by R1. And so R1 is pointing to this address. So the current value of R0 will be stored into this address. Okay, so this is the GPIO digital enable register. And you can find this on page 689 of the datasheet. Now, the GPIO digital enable register GPIO port E APB base address. APB stands for Advanced Peripheral Bus. So the base address for port E is 40024000 hexa, and the offset is 51C hexa. It's a 32-bit register, but only bit 0 to bit 7 is used for the digital enable register. Next is the GPIO alternate function select register, and you can find this on page 671 of the datasheet. And the GPIO port E APB base address is 40024000 hexa, and the offset is 420 hexa. It's a 32-bit register, and the alternate function select register is taking up only 8 bits, that is bit 0 to bit 7. Okay, so next, these 3 instructions here, basically the purpose is to disable the analog function. So the first instruction here is the load instruction. Basically, this will copy the address or value assigned to this symbolic name, which is this value 400245528 hexa. So this will be loaded or copied into register R1. And then the next instruction, which is a MOVS move instruction, will copy this decimal 0 into register R0. And then the store instruction will store the current value in R0 into the address pointed to by R1. So R1 is pointing to this address. Next, we have these instructions here that will configure PE4 and PE5 for UART operations. Again, so we have this familiar load instruction. This will copy this value, hex value that is assigned to it, which is 4002452C hexa, will copy into register R1. And then this load instruction will copy this value, all right, this hex value into register R0. Now, this value 00110000 hexa basically is to configure configure PE4 and PE5 to work as UART pins. So each 4-bit field in the PCTL register specify the alternate function for a particular pin. So in this case, it's PE4 and PE5, and that will select the UART operations. And then we come to the store instruction. So we store the current value, which is this one, in R0 into the address pointed to by R1. The R1 is pointing to this address. And then the BXLR will return the control back to the main routine. And END here, all right, the END function, directive will marks the end of the entire subroutine. Now, this is the GPIO analog mode select register, and you can find this on page 687 of the datasheet. And the GPIO port E APB base address is 40024000 hexa, and the offset is 528 hexa. It's a 32-bit register, and it's utilizing bit 0 to bit 7. And next is the GPIO port control register, and you can find this on page 689. As before, the GPIO port E APB base address is 40024000 hexa, and the offset is 52C hexa. It's 32-bit registers, and all 32 bits are utilized for this port control register. Okay, so we've come to this UART5 transmitter proc subroutine. All right, so this subroutine is responsible for transmitting a character using the UART5 module. So let's take a look at the first instruction. This is the familiar load instruction. This will copy this address, which has been assigned to this symbolic name. So this address 400110018 hexa will be loaded or copied into a register R2. And then we come to this part, wait underscore tx underscore empty. Now this part here, let's take a look at this load instruction. Basically, this will copy the contents of the address pointed to by register R2, and register R2 is pointing to UART5 underscore FR, which is this address. So whatever's in this address will be copied or loaded into register R1. And then we come to this AND instruction. Basically, this is a bitwise AND operation between register R1 and this hex value 20 hexa. And this is basically to check if bit 5 is set. Now, when bit 5 is set to a 1, it means that the buffer is full and the UART cannot send any new data until the buffer has space. All right, so and then we come to the compare instruction. Basically, this will compare this compare operation is to compare the result of the previous operation to 0. If bit 5 is set to a 0, it means that the transmit buffer is not full and is ready to accept new data. And then we come to the BNE instruction. This is a branch not equal instruction. So if the buffer is full, you keep waiting. All right. So that's what it means. Okay. So next we come to the next part. This is these instructions here. These two instructions will transmit the data in R0. So basically, this load instruction here will copy the address assigned to this symbolic name, which is 400110000. So that will be copied or loaded into a register R0, and the store instruction will store the current value of R0 into the address pointed to by R2, and R2 is pointing to this address. So then we come to the BXLR that would return this instruction here. You will return the control to the main routine, the calling routine. Then we have the align instruction, align directive, is used to ensure that the code is aligned on a word boundary. That means 4-byte boundary for proper performance and efficiency. And END marks the end of this procedure of subroutine. And END directive basically marks the end of the entire program. Okay, so this is the UART flag register, and you can find this data on page 911 of the datasheet. Now, the UART flag register, the UART 5 base address is 4001 1000 hexa, and the offset is 018 hexa. It's a 32-bit register. Only bit 0, bit 3, bit 4, bit 5, bit 6, and bit 7 are used. Then we come to the UART data register, and you can find this on page 906 of the datasheet. And the UART 5 base address for this register is 4001 1000 hexa, and the offset is 000 hexa. It's a 32-bit register. Bits 0 to 11 are used for this UART data register. Demonstration. Now, for this demonstration, this is my setup. All right, so this is my TM4C series launchpad board. This is a mini breadboard. Here is the USB to TTL adapter cable, and here is the logic analyzer. Now, let's take a look at the connections. Now, from the TM4C series launchpad board, let's look at PE5, port E, bit 5. Now this is the TX pin on the TM4C series board. So this is the transmitting pin. Now this is then connected to the RX cable of the USB TTL adapter cable. All right, so transmit, receive. And the receive pin of the TM4C series launchpad board, that is pin PE4, which is this one, port E bit 4, that is connected to the transmit part or transmit cable of the USB TTL adapter cable. All right. So RX to TX. And then we have the ground of the launchpad board to ground of the USB TTL cable. Ground to ground. And then the TX pin of the TM4C series board is connected to D0 channel of the logic analyzer, and the ground pin is also connected to the logic analyzer. All right, so this is the connection. Oh, and not to forget the USB power connector, which is up here. So don't forget to connect that. And so this is a picture of my setup. Now, in addition, you will need a terminal emulator. I will be using TerraTerm as shown here, or you could use PuTTY, or you can use RealTerm.
Okay, so I've started my Kyle Microvision IDE, and I've uploaded the code here. So this is the initialization part of the code, declaration of all the registers used with all the addresses assigned to the symbolic names here. Then we have the main routine here. Then we have the three subroutines. The first one is enable clocks. All right, so this is the enable clocks proc subroutine, then followed by the initialize UART5 proc subroutine. It goes down, and then the third subroutine is the configure UART5 proc subroutine, and then we have the UART5 underscore transmitter proc subroutine here, and this end here indicates the end of the entire program. Okay, so that's the code. So what I'm going to do is I'm going to go to a project and then build the target. Here we have 0 errors, 0 warnings, and I'm going to upload the code to the TM4C series launchpad board. Let me just... Alright, so here's the board, my setup. Let me just open it up. So here's my setup here. So let me upload the code. And we have programming done, verify OK, flash load finished. So what I'm going to do now is I'm going to let's look at the output on the TerraTerm, on the terminal emulator TerraTerm. Just give me a minute. Let me just find my TerraTerm. Break it across here. Alright, so I'm going to hit the reset button here on the TM4C series board, and watch out for the output on the terminal emulator. Alright, and we see the word hello being displayed. Let me just press the reset button again. Alright, a second hello, and let's do it one more time. Alright, so this is what you will see on the terminal emulator. Alright, when you press the reset button on the TM4C series launchpad board. Now, let's move over to the the logic analyzer output. Alright, so let me just, oh sorry, wrong one. Yep, alright, so here it is. Now I've already set it up prior to all this so that, we don't have to waste time setting it up. So what we have here, this is channel D0 of the logic analyzer. And these signals that you see, this is coming from PE5 of the TM4C series launchpad board. So these are the signals, alright, coming from the board that is pin PE5. Alright, and so these are the signals, the digital signals coming out from PE5. Now, this top bit here, alright, these are what they call the protocol decoded output. And what we see here is the word hello, H-E-L-L-O. And these are the binary equivalent of the ASCII H. This H here is in ASCII. Alright, so these are the binary representation of ASCII H. Now, the hex value for uppercase H for ASCII H is 48 in hexa. Now, if you translate the binary, these are the binary, but the binary appears to be in reverse order. That's because, if you recall from our early discussion, that the least significant bit, which is this one, get transmitted first. So hence, the output appears to be reversed. And remember, there is this start bit. Let me just. So this is the start bit, and this is the stop bit. And we frame, and we did this frame here between this point and this point are the data, which is the binary of the ASCII uppercase H. Now, if you look at 1, this is the output from PE5, and another 1 here, and these are all zeros, so this is all space here, 2 zeros, space, and this last 0 is a space, frame between the start bit and the stop bit. So this is the output from the logic analyzer.
Okay, so that's it for this video. I hope you have found this video useful, and I'll see you in the next video. Bye.